But today what we're going to start to look at is electrical circuits. We will be able to find the voltage drops in various circuits. And what we're going to do is we're going to explore how circuits sort of work, how the current, the voltage laws that we've just spent all this time talking about, how they apply. So essentially the first couple of lessons about electricity were looking at V equals IR. We're building up to V equals IR. And the reason is because we need these to understand electrical circuits. Now, when we want to talk about V equals IR, we need to first talk about what current is. So current is the movement of charge. It's like the flow of a river, the movement of charge as it goes from one place to the other. We talked about voltage being the energy these things have. It's the push that makes these electrons move from one place to another. And the last thing we talked about was the resistance. The resistance is the things that stop the electricity from moving, that stop the flow. It's like a rock falling into a river. It doesn't matter, you know, if a rock goes into a river, it's going to slow how quickly that river moves through. It's just going to not move as quickly. It's going to, and if you want to move that river as quick as it was, you have to put more energy in. You have to, you know, push more water down your river or make a bigger waterfall. Now, towards the end of the last lesson, what we talked about was we also talked about parts of the circuit. So we went through these parts in one lesson really quick. And then we talked about a battery, which one's positive, which one's negative. Then we talked about voltage drops. What does a voltage drop mean? Voltage drop just means this is a place that a circuit will lose energy. This is a place where the electrons will lose energy. And we're going to talk about what happens in this lesson, believe it or not. We're going to talk about what happens if there isn't a place for the circuit to lose energy. That's going to be something interesting. And then voltage drops, although there is, the other thing we normally assume is that the voltage drop through a wire is 0, because we just assume that there's very little resistance. We then jumped in and talked about how to solve. These are some things from electronics 1 that I gave you. Then we talked about series and parallel circuits. What are the differences? Series has one path, parallel has multiple paths. Series is dimmer than a parallel circuit, which is usually brighter. Why this is the case? Because a series circuit you'll end up dropping, say, 3 volts and 3 volts for a 6-volt start. But for a parallel circuit, because you're starting with 6 volts and splitting, you'll lose 6 volts here, you'll lose 6 volts here, and then ultimately at the end you'll have 0 volts. So then these guys are brighter because they're losing more voltage. Now, interestingly enough, it actually doesn't matter about the current. Okay, remember the voltage is the amount of energy lost. The current's just how quickly that's moving through. So even though this guy at the top has less current than this guy here, because it's just losing more voltage, it's brighter. I said the order doesn't matter. Of the if you will lose 2 volts. If you have 10 volts, you will lose 2 volts here and 8 volts here. You will lose 8 volts here and 2 volts here. Doesn't matter which one comes first, because ultimately electrons are lazy. This is going to be the other motto of today's. Electrons are lazy. They want to lose as little energy as possible. So if they want to lose as little energy as possible, they're going to lose as little energy as it takes to get through a 2-ohm resistor, and that is going to be 2 volts or so on. Now, I did an example with you guys with some turning wheels and some water to sort of describe why order doesn't matter. And I went away from it after teaching it, and I was a little bit disappointed in myself because I thought I still probably did that in a really confusing way. I still haven't, and I'll admit I still haven't found the way that works for me yet to try and explain this in a way that makes sense. I'm going to try another method, another technique, to try to describe this. And I just want you guys to watch this, okay? If it doesn't make sense to you, that's okay. On this, we're going to do another analogy. Instead of the water analogy, we've got a man, and the man that's running, he's just going to represent an electron, okay? Now, as that electron moves through the circuit, it's going to start off with some amount of energy. And at the end, it's going to finish with no energy, 0 volts. And as it goes through the circuit, we've got some resistance here. The resistance in this case are these hurdles that it's going to have to jump over. Now, those hurdles are the same size. So they are the same level of resistance, okay? So I want to show you this example first. He's going to, he thinks, he's thinking to himself, I'm going to use 10 volts. Okay, fine. You're going to start off with 10 volts of electricity? Sure. 10 volts of energy? Go nuts. So what does he do? Here he goes. He jumps. Okay, yeah, we'll keep going. Oh, great. He's tired. Okay, why is he tired for? Because he spent 7 volts with that big jump to get over that resistor. And then, all right, so he's tired. Okay, so then he keeps going very slowly and he climbs barely over that second resistor. How much does he lose over that second resistor? He loses 3 volts to get over that second resistor. Okay. So the problem that we have with this is that this is completely wrong, okay? This is not the way that it actually works. The reason it's not the way that actually works, and a lot of people go away and they think, oh, well, you know, this is the way that students usually write down an answer to how it works. And the reason that students write this down is because my opinion is students think about their own thing. They think if I was running through a race and I met a piece of resistance like a hurdle, I would spend a lot of energy climbing over at the start. By the end, I'm going to be tired. I'm not going to spend as much energy to go over the next hurdle. And it's like, that's how students think that electricity works. I'm always having to tell them, no, that's not how the electricity works in this circuit. The main idea is to remember that electrons are lazy, okay? Now, if electrons are lazy, what that means is that, so write that down. What that would mean if electrons were lazy is this. How much energy, how much voltage does it take to get over the resistor? If electrons are lazy, how much does it take to get over the resistor? Can someone tell me what they think? How much energy does it take to get over the resistor? Given that it lost 3 volts on the right and 7 volts on the left. You can write the answer in chat or anywhere, I don't care. But I want you guys to tell me, how much energy do you think it takes? Any answer will do.
Isn't it 5 and 5?
Yeah, it's close. Yeah, well, I'll show you what I mean. In this example here, you would be right. You could spend 5 volts if you had 10 volts, but I'll show you. Angus. Don't make me kick you out of the stream. For being disrespectful. If you look at this example, you've got 3 volts, right? That he needed to get over it. So in theory, all he needs to get over this resistor is 3 volts. He's wasting 7 volts here. He's wasting more energy than he needs. So what's the alternative? The alternative is to instead say, well, why don't we use 6 volts? Because if I use 6 volts, they can spend 3 volts jumping over the first resistor and 3 volts jumping over the second resistor. Why? Because that's the least amount of energy needed to get over the resistor. That's the littlest amount of energy they need, okay? They don't need to spend 7 volts, they need to just spend 3 volts. And that's because, again, electrons are lazy. They want to spend as little energy as possible to get to the other side of the circuit. So therefore, if they can get away with spending 3 volts, then that's exactly what they'll do. And if they had less than 3 volts, let's just say this runner only had 5 volts, well then maybe they might not be able to complete the circuit because maybe the voltage, the resistance is just too high. And that can happen sometimes. So that's the main thing here. Now we could answer, so this example on the bottom uses the least amount of energy to ensure that it reaches the end. The least amount of energy it needs is 6 volts, so it spends 3 volts to the first one, 3 volts to the second one. If it was uneven, like if it spends 7 volts in the first one and 3 volts in the second one of these two is wasting energy. There's this one. You would not, and electrons don't waste energy. They're not going to waste 4 volts of electricity if they can get over that jump in 3. Now, you could have something wrong here. Okay, so hold on guys, this guy's complaining. He wants to use 10 volts of electricity. All right, well, he actually can use 10 volts of electricity to get through this instead of 6 volts like the guy on the bottom. But we've got to be careful about how we do it. So I'll show you how it works. So how it would work, all right, we'll let him go, is that he would run just like he did before. But the difference is of course he will drop 5 volts at the first one and 5 volts at the second one. Yes, this is what Sang said before. But the reason is that it uses more energy than is needed per jump compared to 3 volts, but it does it faster. Because it's got more energy, these electrons can move faster. And because they move faster, then they're going to the whole circuit's going to work really well. Now, if it was 20 volts, then you would lose 10 volts at the start and 10 volts at the end. And again, it would move even faster still. As you increase the voltage, it's just going to spread it out evenly because they're the same resistance. They don't want to waste energy on one and not the other. They would rather use the same amount of energy, and they would make it go faster. Now, when I talk about, when we talk about these kinds of things, I know that I keep saying, oh, the electrons know what's going on. And I know that some of you guys are thinking that electrons don't have a brain. You're right. Electrons don't actually have a brain. The reason that they would drop more voltage is because it's just, there is a resistance. How much do I need to get through this resistor? I need this amount of voltage to get through this resistor at this speed. So if I have more voltage, I can get through that resistor faster. Okay, so Angus saying you need to focus on the lesson. I'm going to kick you out. You can have a private conversation elsewhere. So yeah, that's the main idea that I wanted to show you guys. I thought it might be interesting to look at this in a little bit of a different sort of light. Hold on a sec. He's just, yeah, let me try. Oh, never mind. I can't get rid of him. Anyway, let's talk about today's lesson. So the first thing I want to talk to you guys about is, again, this idea of being lazy. And this is going to build up this idea of what happens when you have different resistors in a circuit? What does that do for the circuit? Well, we always refer to things as the path of least resistance. Electrons are lazy, and essentially they want to try and get to the positive side of the battery in the least amount of energy possible. So one example that I usually do to do this is I usually talk about this make-believe idea. We're going to have a mountain here, right? And at the bottom of that mountain, we're going to have two paths to get from one side A to the other side B. And the other side B, we're going to have a bunch of students. We're going to make these high school students. You know, they're all over at A. And they want to get to B, and they can either go over the treacherous path that goes up the top and to the bottom.
So that looks like poo.
Yeah, yeah, I can see that.
Can you add some lines, not a fly or two?
Hmm?
Like, you know, the stink lines?
Yeah, no, we're not adding stick lines. So
Oh,
students can
fly?
either take this path to go over the mountain, which is going to be really, really difficult, or they can instead walk around the mountain, which is really, really quite easy. It's just a nice little path that goes this way. And yeah, and in the end, it gets to B. We're going to put, I don't know, we're going to put an ice cream shop at B. So, you know, the students actually want to get to that ice cream shop. Now, here's the question. Students, just like electrons, are lazy, right? They are going to have a choice here. They can either walk over the top of the mountain or along the path. Which way are those students going to walk? It's which way are most of them going to walk? What do you guys think?
Over. Well, you say they're lazy, so wouldn't they get around?
Exactly. The majority of students are actually going to go around the bottom of the mountain because honestly, they're lazy. They're not going to want to go this high, you know, climb a mountain to get over it. They just want to walk the easiest path possible. Now, you will have one or two crazy students. They're like, I want to go over the mountain because I don't want to be near all these other guys. But there's going to be I don't want to be near these other people. But that's going to be very, very few. There aren't going to be many people. And that's because students, just like electrons, will always take the path of least resistance. This path down the bottom has less resistance because it's really easy to walk down this path than this path at the top. This one has lots of resistance. Now, let's use our electricity term here. The path of least resistance has high current. There are lots of students here. The path of most resistance has low current. I've actually seen this in real life. One of my friends at school, I've seen this a lot. If you actually look at the back of D14, there is a path there that's pretty much mud, which students who have tried to take a shortcut to go from the science center to D14 have walked through the grass and then made a path. And it's the path of least resistance. And you say, well, why aren't the students walking along the concrete path around the other end of this to get to D16? It's like, well, because students are lazy. They're just going to cut across the grass because it's faster. So this is the same idea that happens in a circuit. If you've got two wires, one that's got, and I'll draw it over here. If I've got a circuit that has two resistors, if one has like 1,000 ohms, well, no, if one has like 1 ohm, the other one has like 1,000 ohms, the majority of the electricity will go through the nice and easy route, and only a little bit will go through the difficult path of highest resistance. Now, this sounds logical, and this actually is how this system works, but we sometimes have a problem. You can end up with a situation called a short circuit. Now, what a short circuit is, and I was always interested in what a short circuit was, because I'd heard it a couple of times on sci-fi shows. And said, oh, you've got a short circuit this, or how you hotwire a car is by short circuiting it. I wanted to know what a short circuit was. Well, more current will pass through the path of least resistance. What a short circuit is imagine if I had a circuit that looked like this. Okay, now I've got a circuit that looks like this, and I've got my electrons, and the electrons are going to come, the current, actually I'll just talk about this current, not electrons. The current's going to come out of here, and then it's going to get to this point here. I was going to say, do I want to go down this branch of that's beneath me that has a light bulb? Or would I instead like to go down this branch that has absolutely nothing in it at all? Well, the current's going to go, I'm going to go down this side here that has nothing on it. And that's exactly what the current does. That's what we call a short circuit. You might think to yourself, so what? That doesn't matter too much. If it's going to, if it's just going to go down a wire. The problem comes is this. Let's say this is 240 volts. When it gets back, it has 0 volts. Now, if there is no light bulb here,
imagine playing Minecraft in class. Oh, sorry, I'm not. Don't worry, sir.
Shush. You should be listening to this. If there's no component
I'm not playing
here,
Minecraft.
you shouldn't be playing Minecraft. You should be focusing on this lesson. If there is
Exactly, that's what I'm saying, sir.
All right. If there's no component here for the electrons to lose their energy, then they will lose their energy into the wire, and they will cause internal resistance in the wire. And what that will do is that'll make the wire really hot. And that can lead to catastrophic failure. Like it can lead to something breaking like that. And a lot of times students accidentally set up a short circuit, and they go, why isn't this light bulb not working? And I'm saying, I'll go around to them and say, are you aware that you've set up a short circuit? Because this light bulb will be off. And students will say to me, but sir, it's connected to the positive end and the negative end, and it should work. And I'm like, yeah, but you've short circuited it, because this wire is a much easier path. Then I'm like, you need to unplug that before that wire that you've plugged in starts smoking. And sometimes, I think once I've actually touched the wire that's connected, and it gets pretty hot. I haven't had a wire catch fire or burn or melt or anything, but yeah, that's, and luckily, because
why doesn't it go to the middle?
Why doesn't it go through the middle?
Yeah, because isn't there like just a straight line?
Yeah, but it's exactly the same idea as the mountain, right? Does the electrons want to go through this light bulb, which is really hard for them to go through, or this wire, which has absolutely nothing, no resistors, no anything? The electrons are going to say, no, screw that, I'm going to take the easiest path. Yes, they could take this path. You've got path A, or you've got path B, but electrons are going to mostly go down path B because it's just so much easier. Now, I'm not gonna, yeah, let's take a little break. When I say a little break, I'm to look at this. I want to show you. So this is what I would do in class. Hold on a sec. Give me a sec. So these are just some videos of people actually short-circuiting things. I think the best one is, let me see, where is it? I don't know. This one, where is it? I think number 3 is the best one. So I'll show you number 3, and then that'll probably be it. So this here, can you guys see the image, the video, by the way, or not? Yeah? Someone in chat or something, can you guys see video? Okay, cool. All right. Now these are 2 high voltage power lines. Okay, in these high voltage power lines, one of them is positive. Oops, I can't annotate. Sorry, I'm so used to. One of these wires is positive, right? And one of them is negative. And of course, the electrons just want to go from one wire to the other wire. And normally it would do that through a house. Like it would go through a house and then go back out. But it just so turns out that a stick has landed on this wire. That means there is now a short circuit. The path of least resistance is not through some person's house with their refrigerator and their washing machine. The path of least resistance is through this stick. And so what does the electron, what do they do? Well, the electrons start moving through the stick. And they zoom in and you wait for it, and it's about now. That is, of course, an electrical arc that occurs because, like, once the stick's burnt up, the only thing left for them to do is to just conduct through the air itself. You get a similar thing, and I think number 2 is the same sort of thing, except it happens much faster.
Mister, I got a question.
Yeah.
What happened if lightning struck your head? Like,
if lightning struck your head, you'd probably die.
really? What happened to those people who got struck by lightning? Oh no, it's lightning.
Lightning is difficult. So
What about the Flash then?
Oh yeah. Nah,
Flash
but
is
actually,
my guy.
what happens when lightning strikes you?
the thing about lightning is this, right? Why lightning kills people is because, and this is actually relevant, so this is why I'm going to talk about it. Lightning comes in, right? And it's what your human body, the trick with lightning is this: it wants to get to the ground. The reason that you get electrocuted is
It
because
goes through your body.
it goes through your body, because you are a path of least resistance. It's easier to conduct through your body than it is to conduct through the air. In fact, that's also why it's really bad idea to go under a tree during a lightning storm, because trees, even though they might provide you shade, are even more easy for it to go through. Now, the reason that people die is because of their hearts. Now, if your heart gets struck by electricity, by high enough voltage of electricity, you will die. So the trick is where it depends where you get shocked. If you get shocked, hit with lightning here, then you're likely to probably survive, because it will go through the path of least resistance and not go through your heart. If you get shocked in your arm, then you might get, it might go this way and you might get lucky and it might go through there. If you got shocked in your head, I'd say that's really bad. One, it's going to cause probably brain injury, but then it's going to go down the path of least resistance. It's going to be straight through your body. It's going to go through your heart. It's also bad if you were holding like a kite with your hand was in the air, because if your hand was in the air, let's just say someone's hands in the air like this, because they draw line. They're waving goodbye to their friend, sure. Then that's going to conduct electricity through their arm. Oops, crap. Draw line through their arm and then through their heart. And that's going to kill them. This is also one of the other reasons why. Just one more interesting side fact. This is what happens when you ask a relevant question. This is why when they're trying to bring people to life using the shock paddles, you know, when they go clear, they try and shock them and they're like, we haven't got a rhythm yet. What they do is they will put one pad for the CPR, the shock here, defibrillator, that's what the word I was looking for, and they put the other pad for the defibrillator down here. Now I know most people are used to putting one there and one there, but they put them like this. And that's because when the shock discharges, they want it to pass through the heart. I actually watched a YouTube of someone talk about this recently. It's like the place that you put them is really important. You can't just put them like on one side of the chest, the other side of the chest. It's usually a good idea to put them under the arm. And that's also where as well they measure your blood pressure and stuff, is they want to make sure that you've got from different sides of the heart to increase the likelihood it will go through the heart. I know that's not completely what you asked for. It's probably a bit random, some of that stuff, but yeah, it's kind of like, I only found that stuff out recently about how defibrillators work, and it's like, yeah, it's interesting. Also, pretty much every single TV show gets it wrong. If you've got a flat line, like, you know, if not when it's like, not this, beep, 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 beep. If you've just got a flat line, it doesn't matter if you shock that person, they ain't coming back. Because it only, shocking a person like that only works if their blood, their rhythm is a bit different. And yeah, I spent a lot of time learning about this just random how.
If it hit a dead body in the right spot, will it come back to life? Will it make the heart beat again?
No.
Saying that there's the answer to your question.
No. So the point is that do all lightning bolts have the same amount of voltage, Reese? No, they don't. Obviously, the voltage of the lightning bolt is going to depend on a lot of things. It's going to depend on, you know, the reason that lightning bolts exist is because, just like how we talked about the other day, when you rub a balloon on something, you can build up a charge. So if you end up having a situation where you've got a bunch of clouds and they rub up against each other, those clouds, when they rub up against each other, are going to, you know, move a lot more electrons to one specific location. So suddenly they're going to be a lot more electrons in one location because they've all been rubbed off each other. And those electrons all want to get to the positive ground. So how do they do that? They jump through the air when the voltage is high enough and they have enough energy to get through the resistance of the air. They will jump towards the ground. And that's what a lightning strike looks like. So you have used the right term about voltage. I guess the problem is that it depends how much clouds, how many clouds there are, how dense those clouds are, how much of those clouds rubbed up against each other in order to build up that negative charge, how much negative charge there is. There are a lot of things that will determine, I guess, how much voltage is in a cloud and how much current there is. So, you know, that might be a thing as well. It's like you might be able to survive a lightning strike from one particular storm, but another storm that's bigger, that lightning strike might kill you. You know, it's hard to know exactly. I'm going to go back to the lesson now, unless there's any other questions. By all means, I'm willing to answer them. I don't.
So one more. So one more. If, let's say, hypothetically, someone got hit by lightning,
Yep.
and then they did come back to life, would they call him Lightning Boy or Zombie Boy?
I would, if they came back to life, the prefix zombie would be more important than Lightning Boy. I think Lightning Boy would be someone that was already alive that got struck by lightning. If they were dead and they came back to life by lightning, it doesn't matter how they came back to life, they're still going to be a zombie. But yeah, I don't. That's my opinion.
Thank you, sir.
Okay, so going back to the lesson. Yeah. So now that we've talked about short circuits, let's talk about electricity in series versus parallel. Okay, now I've spoken about this briefly, so I guess it's time to actually deal with it. In a series circuit, firstly, the current is the same. The total current is the same throughout the whole circuit. If I was to have a circuit, let's draw this down the bottom left here. Let's say I've got a series circuit. I've got two resistors. The current here is the same as the current here, is the same as the current here. The current is always the same because ultimately there is nowhere for that current to go. Okay, it's just the same wherever you go. The resistance is different. The total resistance is equal to the sum of each resistor. So if this one down the bottom here was, say, 3 ohms, and this one was 5 ohms, you would just, the total resistance is 8 ohms. You could, instead of having a 3 ohm resistor and 5 ohm resistor, you could just replace that with an 8 ohm resistor and everyone be happy. The voltage total, the total voltage, if this is 12 volts, then maybe this is, this could be whatever. Let's say this is, sorry, 12 volts, and this might be 8 volts, and this might be 4 volts. The total voltage that is dropped over the circuit is equal to the voltage in the battery. So these are the 3 rules that we need to talk about, and we're going to bring them up a lot. So the total voltage, the voltage dropped over the whole circuit, you just add each individual part. The total resistance is easy. You just add each resistor to get to the total resistance. The total current, don't even need to worry about the total current because the current is the same everywhere. Series circuits are easy to calculate because you just got to like pop them in. Where they
Wait,
get...
Mr. What does R stand for again?
Yeah, what's your question?
Bro, what does R stand for?
Resistance.
All right.
So this is current, resistance, voltage. Now this is where it gets hard, is parallel circuits. Now parallel circuits have got a mind of their own. Parallel circuits, the current in each branch adds to the total current. And I'm going to go through an example of that maybe in a second. Actually, I'll do it now. So that means if I've got 10 amps, okay, and let's just say that splits, and I have 4 amps in the bottom. What do you in the top? What do you think I've got in the bottom? What current do you reckon is going to be here?
Current.
Someone said on chat. I need to open it up. 6. Beautiful. Easy. So
Why 6?
yeah, it's 6 because it has you can split the current, but you can't just split it and leave like some of it left over. 10 minus 6 is 4. Now when these two wires come back together, the end current is going to be 10 amps again. because that's how it works. So with a parallel circuit, that's how current works. Now resistance is hard. Resistance looks like this. The total resistance is equal to the reciprocal of the total. Let me say this correctly. The reciprocal of the total resistance is equal to the sum of the reciprocals of each resistor. This formula here, I'm going to show you a specific example. Okay? So don't stress too much about it, but this is how you calculate the resistance total. In the left, it's nice and easy. You just got to add each resistor. In the right, you can't just add each resistor. You got to add 1 divided by each resistor and then flip it over at the end. Good news though is that the voltage is easy. The voltage is easy to calculate. Each path through the circuit must have a voltage drop equal to the voltage drop of the cell. So what I'm going to do is, as I explore how different circuits work, what we're going to be doing is we're always going to be starting with series circuits and then finishing on parallel circuits, just because they're a little bit more hard. Okay? But ultimately, they both follow the same rules. Okay? You can't, they both follow, and the main rule that they both follow, whether you've got series or parallel, is V equals IR. Doesn't matter which circuit you're looking at. Okay, so let's now look at this guy. Let's look at an example of this current resistance rule here, and then we'll jump in. So resistance in parallel. A parallel circuit has a resistor measuring 2 ohms and another resistor in parallel measuring 5 ohms. What is the total resistance? So how you calculate it, okay? Watch carefully. A parallel circuit has resistors measuring 2 ohms and 5 ohms. That means that the total resistance, the 1 over the total resistance, is equal to 1 over 2 plus 1 over 5. Now, hopefully, by the time you've reached this level of mathematics, you're somewhat comfortable with fractions. Not everyone is, though. But so this is going to be during the test. I always watch students. I can tell which ones are comfortable with fractions and which aren't.
Is it 10 over 7?
Sort of. Let's grab a look. 1 over RT is going to be 5 over 10 plus 2 over 10, which is 7 over 10. Perfect. Now, in order to work out what RT is, you need to flip over both of those. So RT equals 10 over 7. You are correct, Sam. 10 over 7 and 10 over 7, the resistance, we have to give this as ohms. Let's do a quick guess here. 10 divided by 7 is 1.43. 1.43 ohms. That means that, and this is the part that always messes with my brain. Was it Brendan? Doesn't matter. What messes with my brain is this. You could instead, so you would have the circuit. So this is what the circuit's going to look like. 5 ohms at the top and 2 ohms at the bottom. You could have this circuit, or you could have this circuit. 1.43. Both of these, you would have the same current and have the same resistance and the same voltage drop. So the resistors are the same. So it's a bit of a weird way to do it, but that's how you would do it for that kind of circuit. One more quick example. Two resistors are in circuit, all wired in parallel. Oh man, this is a challenge question. Okay, the first resistor has a resistance of X. The second resistor is twice as large as X as the first resistor. What is the total resistance of the circuit in terms of X? Does anyone want to give this challenge a go before I give the answer? I'll give you guys a minute to see if you can work it out, what the total is. I'll quickly work it out myself, just so I can make sure that I've got the answer. Man, yeah, this is really... okay. What do people say? Did anyone get the answer correct? Because it's a bit challenging. Oh, wow. Looks like Brendan and Jason, I think, have figured it out. Good job. Looks like we've got some smart cookies in this class. Right. How would you do it? 1 on RT equals 1 on X plus 1 on 2X, because one of the resistors is double the first resistor, so we're at 2X. Great. 1 on RT. Now I can't add these together because they're not the same denominator. So 1 on RT equals 2 on 2X plus 1 on 2X. If I multiply the top and the bottom by 2, now I can add them together. 1 on RT equals 3 on 2X, or RT equals 2X divided by 3. That is a bit challenging. Considering that you guys got that, is pretty impressive. So yeah, hats off to you. Let's keep going. We're going to do, we've got now, I don't want to spend too long going through this with you guys because I've already spent a lot of time talking. What I'm going to do, I've already talked for about an hour. What I'm going to do is I've got 1, 2, 3, 4, 5, 6, and the challenge questions left. So what I'm going to do, but if you look, I've actually split it up into a different section. So we're going to do questions 1 and 2 together first. If you're in the process of copying notes by drawing them, I would suggest drawing this down. We're going to look at this specific circuit, and we're going to try to understand everything about it. Going to give people a second just to look at it, make some guesses about it, and then what we'll do is we'll answer it, and yeah. Okay. When I look at circuits and I do questions like this, I usually go through it in a bit of a process. Okay, that process involves looking at the voltages, looking at the currents, and looking at the resistors. Okay, because and I'm going to do this in 3 parts for this lesson. And so we're going to do this first. We're going to look at the voltage. We're going to look at, now, you know what first we're going to do? We're going to do the resistance first. So we're going to look at A and B. These are light bulbs. Okay. So the resistance through A, can someone tell me what is the resistance through A? What is the resistance through light bulb A? Someone just said it. It is 4. Yep, beautiful. 4. By the way, someone asked what's voltage drop. Voltage drop just means how much energy or how much voltage it's going to lose as it goes through each. So resistance A is 4 ohms. Can someone tell me what's the resistance through B? I know this is easy, but it's still got a point. 4.
4.
Easy. Nice. Resistance
Okay.
through B is 4. Who can tell me what the total resistance is? Remembering this is a series circuit.
8.
Beautiful. 8.
Oh, man.
Because this is and I'm using RT, because this is a series circuit, you add the resistors together. All right, that's resistance done. We have now calculated all the parts that we need to know about the resistance. Let's talk about the current. Now the current I'm going to do in maybe green. The current. Now, the current, we want to know what the total current is. To work out what the total current is, we need to know what the total yeah, no, Brendan's got no, yeah, I have already taught you guys, saying it's he's just one step ahead because he's figuring this stuff out before you've gotten there. So how we can work out the total current is we can use a formula. We know, because it doesn't say the current here. If I look here, it doesn't say the current. You know what? Let's actually do one thing before we do the total current. Let's look at the voltage for a second. We don't know what the voltage to RA is because it's not written down. We don't know what the voltage to RB is because it's not written down. But we do, but we do know what the total voltage is. Can someone tell me what's the total voltage? It's written down there, right? Easy for us to see. Someone said it. 6 volts. Beautiful. The total voltage is 6 volts. Now, the total current is a little bit challenging is the first one that we need to do some calculations, well, some serious mathematical calculations to work out. We know the total resistance and we know the total voltage. So therefore, we can actually say V equals IR. We want to calculate I. So V divided by R equals I. All I'm going to do now is this. The total current is equal to the total resistance divided by the total voltage divided by the total resistance, which means that the total voltage being 6 volts divided by the total voltage being 6 volts divided by the total resistance, which is 8, is going to be 0.75 or 3/4. So that's going to be 0.75 amps. Now, the current through resistor A and resistor B are also going to be 0.75 amps and 0.75 amps because it doesn't matter whether the electrons go through, it doesn't matter where they go, there's only one path, so they have to have the same current. Okay, now a lot of this stuff is extra. You don't necessarily need to solve it every single little itty bit. I'm just trying to show you guys every single little itty bit so that when you get down to it and you have to solve it yourself, if you want to follow this process, you can probably get the answers to any question. The last bit that we need to do is work out the voltage drops. Now, the voltage drop through resistor A. Well, the voltage through resistor A is going to equal the current through resistor A times the resistance of resistor A. V equals IR. What is the current through resistor A? Can someone tell me what is the current? What have we written down? What is the current through resistor A? 0.75 amps. And the resistance of resistor A is what? 4. If I go 0.75 times 4, then that's going to give me 3 volts. Beautiful. And if I do the same thing, I can do the same thing for resistor B and get 3 volts and 3 volts. That means the amount of voltage that gets lost over the first resistor is the same as the amount of voltage that gets lost over the second resistor, which makes sense because they're the same resistance. It also is quite nice that 3 volts plus 3 volts equals 6 volts. That's exactly how many volts are in the circuit. So that means our problem works out. There is a lot of working out here. You don't necessarily need all of it. You, in fact, if you are really quite smart, you could probably clue in quite quickly and figure out, well, if they're the same voltage, then they're going to split. If they're the same resistance, they're going to split the voltage equally. So, 6 divided by 2 is 3. That's how you could quick and easy work it out. But ultimately, working out the total resistance and the total current are 2 of the main steps you need to do for this. Are there any people that have any real questions that they can say, I don't get this, I don't understand this part here? A lot of this is going to have to be done with the assistance of a worksheet. So when I give you guys electronics 2, probably on Thursday to work on, I'm probably going to be sitting in this Zoom meeting for the whole lesson, just answering questions, not even like teaching guys, because I know this is a topic that requires some work. We're going to do one more example and that's it. We're going to do example 2. Now, if you look, example 2 looks pretty much the same as example 1, but there is a little bit of a difference. Difference being they're different size resistors. One of them is really easy for the electrons to get past, and one of them is really hard. If I call this one resistor A and resistor B, which one is easier for the electrons to get through, A or B? A is easier. So which one's going to have a greater voltage loss or a greater voltage drop? Because B, exactly. We should be looking at B for when we calculate this. B should have a greater voltage drop. It's going to require more energy to go through this light bulb compared to this light bulb. Let's work it out. Okay, first things first. Let's start with resistance. Can someone tell me what is the resistance to A, B, and the total resistance? Someone's already on board. Okay, Jason's on board. A is 1, B is 4, total is 5. Does that make sense to everyone how we got these values? Yep, Jess gets it, Jason gets it. What about you, Julia? Does it make sense to you? I don't know. You can write down in the chat if you want, Julia, but I want to make sure that you get it too. And I haven't really, yeah, resistance is easy. You're right, Lisa. Resistance is easy at the moment because it's written for you. Trust me, it's going to get a little bit challenging a little bit later on. Let's jump in and now look at a different one. Let's look at voltage. If I do VA, well, there's nothing written down for VA. I can't do VA. VB, well, there's no voltage drop for VB. I can't do VB. What about the total voltage? What is the total voltage of the circuit? 6. Thank you, Emre. 6. Yeah, that's fine. 6 volts. Sorry, Julia, you're cool. I saw that. So that's cool. That's that. Okay. So that means the last one to look at is the current. The current. The current, well, we don't know what the current through A is. We don't know what the current through B is, but we can work out what the total current is. We can use the same formula we used before. The total current is going to equal the total voltage divided by the total resistance. And we got that because V equals IR. Dividing both sides by R gives you I. Now the total voltage is 6. The total resistance is 5. 6 divided by 5 is 1.2 amps. So that gives us our IT, 1.2 amps. What is IA? What's the current through A going to be if we know that it's if we know, so we're going to wait for someone new because I'm not sure if you guys are answering the previous one or later one. What's the current through A? Beautiful, you're right. The current through A is going to be 1.2 amps. And what's the current through B going to be? 1.2 amps. It doesn't matter because it is a series circuit. The current has nowhere else to go. So the current is the same. Once you know the current for the first one, the second one, the third one, we can now just quickly work out the voltages for the little ones. Let's go back to blue. The voltage through A is going to be the current through A times the resistance through A. Is going to be 1.2 times the resistance through A is 1. That's going to be 1.2 volts. The resistance through B is going to be the current through B times the resistance of B is going to be 1.2 times resistance through B is 4. That's going to be 4.8 volts. And now we've done the voltage drops, we've done the currents, we've done everything that they could possibly ask for this circuit. So why this is good is because we actually proved our hypothesis. We said that this one being a larger resistance is going to need more voltage to get through, and that's exactly what we worked out. The 4 ohm needs 4.8 volts, whereas the 1 ohm only needs 1.2. We add these two together, then I get 6 volts. Now, if I've got some real math nerds here, there is another shortcut way to do this. You could think about this being, okay, I've got to share 6 volts against 5 ohms, so you can just go 6 divided by 5, which is going to give you 1.2 volts at the start. And then that would mean that's 1.2. This one has to be 4 times 1.2. That gives you 4.8. That's another way you could solve these problems. I will usually use that shortcut in simple questions like this, but because for you guys, you have never done this sort of level of in-depth resistance measurements before, I don't really want you to necessarily do that, but if that's what you're doing, fine, and you show me that you understand this. I'm not going to go through this. I will quickly mention this. Just this is the third one. We'll do this tomorrow, I think, because I give you guys a little bit of a break at the end of the lesson. Reese, I'm putting this one up there for you, Reese. If you hear, I'm looking at you, not actually physically looking at you because I'm looking at my laptop screen. But if you can hear me, I'm looking at you, because this is an example where the resistance is not easy. See how they haven't given you one of the resistors, okay? But believe me, even though they haven't given you the resistor, you can still solve it. And trust me, Wednesday at 11 o'clock, I will be showing you how to solve the next few. Yeah, that's right, Reese. I was talking to you. Be afraid. Yeah, but it's not. It does look a little bit harder, but it's actually not that much more challenging. It's just the only difference is that you've just got to go. And the other thing about these problems is that, especially for this example, which I'm going to do on Wednesday, is that there are always multiple ways to solve these problems. Okay, for example, with this example here, remember that last step, how I did this here? Believe it or not, get this, there is another way you could solve that. There are so many different ways to solve that. I just showed you the sharing way, but there's another way. If I know that there are 6 volts in total, and I know that I've already used 1.2 volts up, if I subtract 6 minus 1.2, that's 4.8 volts. There are always, and so instead of going IB times RB, I could just do that instead to work out the answer. There is always a different way to solve these problems. I'm going to show you probably the slowest and most boring way, but the reason I'm doing that is so that you guys get sick of it and go, you know what, sir, I'm going to do my own way. And when students tell me that, I'm like, good, do your own way. Maybe you get the answer faster, and which shows me you understand it. And if I can get my students to understand it, I don't care what way you use. You could instead, you could look at an individual resistor to work out the total current. But yeah, that's why when I put up this, I'm like, this one here that we're going to go through on Wednesday has multiple ways to solve this. I can think of 2 ways. We could work out the total resistance and then find out the resistance of the first one and then use that to find the voltage drop. We could find the voltage drops and then use that to find the resistance. Just, so many different ways we can do it. I haven't even decided which way we're going to do this one. But when we do it on Wednesday, you guys will see. On Wednesday, I think what I'll do is try and get through the last 4 of them. So I'm going to try in one single period to go 1, 2, 3, 4. If we run out of time though, then maybe I'll just do, maybe I'll save this last one for next time. But yeah, and then on Thursday, the goal will be just to spend the whole lesson, you guys getting some practice with these and actually trying to work them out. Can the resistance work? Ooh, good question from Reese. Can the resistance work if can the circuit work if the resistance is higher than the voltage? And the answer is yes. The first example is that we can see that is we can even go just back to the one we just did. Look at this. The total resistance, Reese, is 8 ohms, but the total voltage is 6 volts. What that means is that, yeah, the total resistance is more than the voltage. All that actually means, believe it or not, is it's actually not that big a deal. All that really means, though, is the current, see how I've got the current over here? The current is actually less than 1. That's what happens when you deal with it. The current is less than 1. In this example here, where the total resistance is less than total voltage, the current is more than 1. But that actually doesn't really make much of a difference. So there's actually no stress. But I can see what your question is. You might be thinking, well, if the resistance is too high, will it still work? It's like, if you get a resistance that's like really, really, really high. So if I had a circuit that had like, you know, 5 volts. And then I got a part here, which is like a 10,000 ohm resistor. You know, you might go, well, what's the current going to be? I is going to be 5 divided by 10,000. It's going to be 0.000005 amps. That's probably not going to mean anything. It's probably not going to be pretty much no electricity moving at all because the resistance is just too high. But, you know, that's something that we can look at later on. Are there any other questions before I end the class for today? Nah, people good. Nope. All right. In that case, I'm going to end the lesson here. Make sure that you have, by Thursday, that you've finished Electronics 1. Make sure you've done the attendance question and uploaded numerical 2. And yeah, have a good night, and I will see you tomorrow.